Hello everyone, and welcome to this video which will introduce present value and future value of an annuity. In this section of the course, we will make the use of two notions that have been seen in previous sections. First of all, compounded interest on a deposit. So if you recall from the sequences application, the value in the future of an amount, V0, will grow at a rate 1 plus I to the power n, where I represents the periodic interest rate and n represents the number of periods between its deposit and the time we're calculating its value. We're also going to use the sum of a geometric series, where a0 is the constant and r is the ratio, and the series is counted for k values going from 0 to n, and perhaps you recall the formula that appears on the right-hand side. By annuity, we refer to constant monetary amounts, so basically amounts that are received, paid, or deposits that occur at regular periodic time intervals with the influence of a constant interest rate. For instance, suppose that Ariana adds $200 every month to a fund that grows with 1% monthly interest. Let's assume furthermore that her deposits took place on January 1st, 2011, and every month afterwards. Ariana never skipped any such deposits, and we're assuming that the rate has maintained its value of 1% throughout. What is the total value of her investment immediately after making the January 1st, 2021 deposit? So this situation fits in the context of annuity because deposits are, first of all, constant in value, periodic, in this case monthly, and the rate is maintained at 1% throughout. So a good strategy to calculate the future value or the compounded value of these deposits that Ariana was making is to use a time scheme. On the time scheme, write enough of the dates and of the amounts to have a global view of the situation. So see here how the $200 deposits are depicted in blue at the dates January 1st, 2011 and until and including January 1st, 2021. Now our strategy here is to find the value of these deposits at the moment or right after the last of the deposits. So we are going to displace the amounts in time. The first of the deposits, $200, is being displaced exactly 10 years towards the future, so 120 months. Therefore, its value will have grown by 1%, compounded 120 times. So 200, 1 plus I to the 120. The second deposit doesn't have quite a full 10 years, but rather 10 years and minus 1 month, so 119 months to gain interest. So 200, 1 plus 1% to the 119. Same goes with the third deposit, which occurred March 1st, 2011, where 118 months of interest are added to the initial deposit. And eventually we'll get to the next to last deposit, which only had 1 month to grow. This is the deposit that took place on December 1st, 2020. And finally, there is the last deposit itself. Since no time span, or no time has spanned since the deposit took place, no interest is added, which explains the zero exponent. So Ariana's total value, or the total value of her cumulative investments, would be the sum of all of these amounts. So here we go. Here is the sum of the amounts that Ariana deposited. Perhaps you'll recognize that this is a geometric series where 200 is a constant term that appears in every one of the amounts that have been added. 1 plus 1% is a constant ratio being used throughout the series, and the exponents k go from 0 to 120. So we can express the total value of these deposits as a geometric series. And thank goodness we have a formula which helps us to find the total value of such a series. The formula, A0, r to the n plus 1 minus 1 over r minus 1. And in this case, r is 1 plus 1%. N is 120, which is the widest time span between deposit and the moment where the future value was calculated. So Ariana would have gained, or her total investment is now worth $46,667. And let's not forget the 82 cents, because every cent matters. Here is a second but very different example that also illustrates how useful geometric series are. In this example, Ariana decides to buy a house. The purchase takes place on January 1st, 2021, and Ariana had to take up a mortgage for an amount of $500,000. This is not necessarily the value of the house, but the value of her loan. So perhaps she made a deposit, and $500,000 is the amount she also had to borrow on top of that to pay off the house. So the $500,000 is her debt towards the bank. To pay off her mortgage, Ariana decides to make payments over the next 20 years, the first of which will take place 1 month after the purchase of the house, so on February 1st, 2021. The last payment will take place on January 1st, 2041, that is 20 years after the house was bought. She will be charged a 0.3% monthly rate of interest along the way. Notice how the rate that is given is monthly, and that concords with the method in which Ariana is paying off her mortgage, which is through monthly payments. So find the value of each monthly payment Ariana will have to make. Just a quick remark, this time you'll notice that the payment is made in the future compared to the moment of the purchase. The house and the mortgage itself, it takes place or begins in 2021, on January 1st more particularly, but payments are made in the future to pay off that debt. So each of the deposits includes an amount that will go towards paying off the penalty as well as paying off the value of the house. To make an appropriate assessment of the payments, all amounts must be compared at one same date. So in our example, given that the value of the mortgage, $500,000, is known on January 1st, 2021, it's a wise decision to reposition our amounts on the time scheme to fit with that actual date. We're going to bring our amounts to date January 1st, 2021 in order to make accurate comparisons. Now remember that if Vn equals V0, 1 plus I to the n can be used to bring amounts towards the future, then we can also take future amounts and bring them back to the past by isolating V0. V0 equals Vn over 1 plus I to the n. So great strategy again is to use a time scheme to visualize what is taking place. So I've placed a time scheme once again where all the payments are listed on the time scale. The first payment on the 1st of February 2021, the last of the payments on January 1st, 2041. And the house itself and the mortgage was contracted on January 1st, 2021. So the last payment, I'm going to work backwards here. The last payment takes place 20 years after the mortgage was contracted. So whatever amount PMT represents, well, 20 years in the future does not have the same value in today's money. So since we're taking a future amount and bringing it back to a present or a past date, that last payment's value in date of January 1st, 2021 is PMT divided by 1 plus I to the 240. The next to last payment, which includes interest, basically moving these elements back is like erasing the interest and finding today's value. 239 months back to the past will provide a new value, PMT over 1.003 to the 239. And then the second payment itself occurred 2 months after the loan took place. So if we move its value back to today's date, when I say today, I actually mean January 1st, 2021, it is worth PMT over 1.003 squared. And finally, the first payment itself is done in the future in 1 month and includes 1 month of interest. So today's equivalent amount would have been PMT 1.003 as the divider. So the sum of all these amounts are in fact used to repay the total mortgage, which was $500,000. In other words, they have to add up in today's money to $500,000, which is also in today's money. So here is the total value of Ariana's payments. Here is the list of all the payments she had made in the future, but recalculated in date of January 1st, 2021. You'll notice that 1 over 1.03 is a common factor of all of the different payments that show up. I could actually have factored PMT as well. So I choose to leave it in that bigger bracket. And perhaps you'll notice that within those square brackets is the exact appearance of a geometric series. In fact, it's the sum of terms that all have PMT as a constant value and all have 1 over 1.003 to the power k as the ratio. And the values of k, the exponent of the ratio, vary between 0 and 239. This is a geometric series, and therefore we also have ways to find the total value of this sum. So here is the comparison we're making. $500,000 is the value of the mortgage. On the right-hand side is the value of Ariana's payments, and of course they are meant to equate or to reimburse the mortgage itself. The summation, the geometric series, we have a formula that we can use to find its total value. What I've done is I've distributed the 1.003 out in the front to the denominator, and that's why the new denominator looks the way that it does. All right, so since our goal was then to find the value of the payments, I've done a little bit of algebra here to isolate the PMT, cross-multiplied the denominator and divided the numerator that accompanied the PMT to find that the payments, monthly payments that are made, are just in excess of $2,900. Slightly different approach, so there's no need for you to use this other approach, but some of you may have thought of doing it this way instead. So we've already built the list of the values of Ariana's future payments, recalculated in date of January 1st, 2021. Some of you may have thought to just rewrite all of these on a common denominator. If you do that, then actually the numerator, perhaps you see it right now, if you read those terms backwards, is already a perfect geometric series that starts with a ratio whose exponent is 0. So actually, I could take the divider 1.003 to the 240 simply out of the summation, and the rest of the addition fits a geometric series with 1.003 as the ratio, varying from k equals 0 to 239. We can then find or use the sum of a geometric series to find the total value of the summation that's taking place. And like we did earlier, we can isolate PMT to find the exact same amount.